So just a heads up, standardizing quiz soon. You probably will have some X bars and stuff like that on there too. So today what we're going to be looking at is working backwards to find areas. So the standardizing formula that I've given you has been basically in words. Value, whatever the value is that you're looking at specifically, minus mean over the standard deviation equals z, right? The number of standard deviations a value is away from the norm, plus or minus. And I think doing this, it's simple algebra here is what we're going to be talking about. So oftentimes we're finding z. We have these three things and we just do the simple math to find z. But what if the mean is what we're looking for, the value or even the standard deviation? Then it becomes a fairly simple algebra problem to solve. So let's take an example of an ACT score. So don't quote these numbers as being exact. I think they're close. Let's say the standard deviation is 4 points. X bar is 21. And let's say that you know that your z-score was 1.13. Let's say this is you. But you don't know your score. So what's your score? Well, we have everything we need to find it. So your score would be the value. I'm going to call that A for ACT score, minus the X bar, 21, divided by 4 equals 1.13. So that's how we would set that problem up. And then we want to multiply both sides by 4. So that we get A minus 21 equals 4.52. Getting rid of the fraction. And then if we add 21 to both sides, we get A, your score, is 25.52. So this is an example where you can solve for your score, but you could use the same approach for anything that's missing. As long as you know 3, you can get the 4th one, right? Okay. And they do tend to throw those at us because they love us, I guess. All right, an idea that's going to be with us for the rest of the year, more than. So when we look at our table A, it always gives us the probability that something is less, of something less happening. So how do we deal with a problem that says, what's the probability that more than this occurs, or something like that, any kind of more than statement? Well, we use 1 minus. 1 minus. So if we look at our score on this ACT test, try to draw a normal curve here. That wasn't too bad. Not bad for a rough Monday morning. Actually, let's not take the ACT test as an example. Let's say that you are 1 standard deviation away from the norm. 1 standard deviation away from the norm. So that's on the plus side where the curve starts to change, right? From going down to flattening out. About there. what's the probability of scoring higher than that? This is, let's not, this is area, by the way. I feel like I'm being confusing here. That's the total area of the curve, right? The 1. So what's the probability of more than one standard deviation? Well, if you look at your table A and you go to 1, you'll find that 0.8413 falls below. This is the table A value. Okay, so 84% of the people scored below one standard deviation. How do we get the more than value? It's going to be 1 minus the 0.8413. It's 1 minus the less than value. Okay. So that means that we have about 0.1587 of the data above one standard deviation away from the norm. And that's right about where remember we took the notes the other day where I did one standard deviation and there was 68% between, but then about 16% above and below. Here's your exact value, but 16% is just fine for an answer. You could definitely say about 16% in this case. All right. So in the case of our 1.13, if we were to look that up, 1.13 is about 87.08%, or 0.8708. For the fun of it, take 1 and subtract that. Okay, I'll do it for you. All right. About 0.1292. Okay? Look on the other side at negative 1.13. What do you find? Does that make sense? Yeah, the area below 1.13 negative is the same as the area above 1.13 positive. So if you're careful, you can use the table and just flip the sign to get that other side, that more than value. Okay. All right. Moving on. You're going to get some questions like this, and some of you are going to get tossed by them. Let's say we have a normal curve. Or approximately normal. Remember, there's no such thing as truly normal. It's just approximately normal or roughly normal or something. And let's say we have some marking spot at negative 0.3 standard deviations and another spot that's at 0.72. And we want to know what's the area between negative 3 standard deviations and 0.72 standard deviations. How do we figure that area out? Well, it's not hard. It involves table A again. What you have to do is you have to understand that table A always gives you the less than value. Always. So the first thing I would do is I'd find 0.72 on table A. Everybody a second to get caught up on their drawing here. that's in a black part, darn it. So 0.72 looks like it's 0.7642. So what that means is that 0.7642 of the data falls to the left of the 0.72. Okay? Now if I look at the 0.3, the negative 0.3, I find that that's 0.3821. So 38% falls below this, 76% falls below that. How do I find the distance between them? Just subtract. Yeah, that's right. So we're going to say 0.7642 minus 0.3821 is going to equal 0.3. Oh, wow. Look at that. Honest, that was dumb luck. So this is going to be the area between. Alright. The next thing I want to introduce, this book's new, you guys know that. So as I'm going through, I'm kind of wondering, when are they going to introduce this idea? When are they going to introduce this idea? And I've been really happy with the way the book's gone, actually very pleased. However, I'm going to introduce an idea a little early. Statistics versus parameters. When I was talked to about taking the stats class, I thought Mrs. Spengler was going to do it. Mrs. Anderson retired. But Mrs. Spengler didn't want to do it because she only has a few years from retirement too, so she didn't want to take on this new class and then have to learn it all and then be on her way. So Mrs. Anderson thought I'd be a good fit. I'm not sure why. Maybe it's my charm and good looks. But anyway, so I sat in on her class starting at the second semester. And I know you guys as students, because I would have thought the same thing as a student, think that, if somebody's a math teacher and they're sitting in on a math class, they must know everything that the math teacher's saying too, right? That's not the case. So my first time taking stats, I took it over a summer at a JC, and it was miserable. The fellow that was teaching it was from another country, so his accent was thick. And near as I can tell, I think he figured that since we were all native English speakers, that all these stats terms made perfect sense to us because, well, it's English, so why wouldn't we know them, right? But each discipline has its own language. So the whole class is like in this disarray of not understanding anything, and this fellow wasn't really doing a very good job of explaining it. So I sat in the back with this other fellow, and we literally went through the book and somehow pulled a B in that class. But I didn't really learn a lot, to be honest. So, and that had been years ago. So I sit in on Mrs. Anderson's class for the second semester, and I'm just as lost as anybody else would be coming into a class at the semester, right? These details have escaped me. Towards the end, I was starting to kind of feel like I'm kind of getting part of it, but there just wasn't enough there for me. So I took the class at BSU. And we got to statistics and parameter. I had seen it with Mrs. Anderson, and then I saw it with my professor, and I could never figure out what the difference was. And so when I started teaching it, I'm going through the book and going through the information and stuff, and I'm like, oh man, statistics and parameter, what is this stuff? And when I read it for myself, for whatever the time it was, it clicked, and I went, how did I not understand that? That is so simple. Okay, so I want you guys not to bumble around with this like I did. Statistics, I think we've kind of defined earlier, they're values calculated from a sample, or data. Yeah, I don't know. Let's just go values. There's lots of things that are statistics. Oops, sorry. Let me get that up there a little bit. Values calculated from a sample. A parameter are values from a population. Now, if your population's small enough, you can find a parameter. Let's say that you want to survey all the students at Centennial High School to find out what their favorite color is, okay? For whatever reason. Well, Centennial High School would be not the sample, but the population. And that population's small enough that given enough time and enough effort, you could question everybody in this school, right? It wouldn't be easy, but you could do it. But for the most part, let's talk about could we question everybody in the United States or even everybody in Idaho and find out on any given moment what the favorite color is of all Idahoans? No, the population's too large, and the population's changing all the time, right? People coming and going, and maybe somebody's on a business trip and you missed them, right? So the values from a population, these usually can't be calculated. Which means generally they have to be given. How they're known, well, that's another story all in itself. Sometimes they're not. So usually a parameter. So a parameter is a population value. A statistic is a sample value. That's all you really need to know. So we've learned some statistical symbols. X bar. What's that? Sample mean. Yes, it is the mean, right, but it is the sample mean. That's why I put that in a little while ago. And we haven't learned the parameter version of that, but I'm going to introduce it today. You probably won't see it for a little bit yet, but I'm going to introduce it. It's kind of a funky M thing. It's called mu. I'm guessing it's some Greek thing or another. This is the population mean. It probably has to be given. It's probably not something you can calculate. And we have SX or S. That's our sample standard deviation. And the population, the parameter version of that, looks like this. It's kind of like a Q with the little thingy thing at the top. It's called sigma. Again, another Greek thing. It's the population standard deviation. And the last one that we need to worry about today is we've learned little n. This is our sample size. And for the population size, we don't use any weird symbols. It's just big N. It's the population size. So mu, sigma, and big N. Mu and sigma, you'll see those a lot. Big N comes up. But I want to introduce those because I keep doing the standard deviation is it uses some of these parameters. So it does something like this. You don't have to write this down. And you don't have to write it down yet, but this is your score minus the population mean over the population standard deviation equals Z. What if we don't have those values? Well, that's when we substitute what we do have, the sample stuff. Okay? So, anyway, those are the notes for today. I'm gonna let you fly and be free. 6 questions?